Welcome to a video on common emitter amplifier design. In today's video we're going to look at the two amplifier configurations, the advantages and disadvantages of each, then the components in the common emitter and what each component's purpose, function or influence might be, then some typical design parameters or specifications that you might encounter, and then we are going to do 3 examples with simulations afterwards to show that the amplifier is actually working. And this video is going to work under the assumption that you know about biasing structures. In video 2 this is covered extensively. Video 4 uses the amplifier analysis, and video 5 is amplifier loading. So those 3 videos are strongly recommended before diving into design. So today we are mainly going to look at the common emitter amplifier with emitter resistor bypassed and the split emitter configuration, so when there is actually emitter resistor present in the small signal analysis and the influences that goes with it. Right, so the common emitter, when the emitter resistor is bypassed, has a couple of advantages. It has a stable Q point because this emitter resistor is for bias stabilization. It has a very large gain, so if you require a large gain, this is the amplifier to go with. And it also has a very large output range. The disadvantages though is that the gain is temperature dependent. It has a very low input impedance depending on your RPi, so your biasing current. Its input impedance is temperature dependent because RPi is beta over GM. And then your design freedom is very limited. You have maximum gain, can't really match input as much. You can't design for a specific gain. Oh, you can, but it's not optimal. So this is a good amplifier for high gains in the end, but it has no stabilization. The only stable part of it is the Q point. Okay, so that's how we get to my favorite amplifier, the split emitter. And the advantages is that we have a stable Q point due to this resistor right here. We can select our gain due to this feedback resistor that we have, which is seen when we have the small signal, the AC part. Its input impedance is increased due to this resistor. It also makes that we can typically select our input impedance. So overall, having this resistor extra gives you more design freedom. The disadvantage is that its gain is decreased from the previous amplifier. Okay, so medium to low gain designs. Then the final one, that's not a disadvantage or advantage, and that's depending on your design, and I will comment on this as we go along, is that your gain can be dependent or independent on temperature. The reason for this is the gain equation, if you remember correctly, was this GMRC over 1 plus GMRE. And the GM is the temperature dependent part here. So if we can get rid of GM, we can stabilize our gain entirely. But for that, GMRE must be much greater than 1, and the equation will reduce to RC over RE. But we don't use it like this because people tend to forget about this assumption right here, and this gain that you get then will not be accurate at all. You need a very large GM REE ratio here for this to actually work. Okay, so um, this is how it becomes temperature independent. And if you ever forget about this equation down here, I won't blame you. Put it out of your mind, but you will see it a lot in textbooks, but it forgets this assumption that you make about it. Okay, so use the top one and everything will always be fine. Okay, now for you to be able to design properly, you need to know the purpose of each component. So I took the split emitter here because if we remove this resistor right here, which is only 1 point, we basically have the other amplifier in any case. So RC together with your VCE here is responsible for your output swing and your gain. Okay. RE1 is your gain not gain stabilization, your bias stabilization. So that is to pin your Q point to the load line. So to have a stable collector current. Right. RE2 has its numerous properties if you add it. So it makes your gain adjustable, increases your input impedance, makes your input impedance selectable when done correctly. And the list goes on. We discussed them in length. Okay, so you can see how this design propagates. Usually you start with a swing and the gain, then you need to stabilize your bias, then choose your gain or whatever you need around that, and then go to these biasing resistors right here. Okay, and typically these are responsible for your bias point or switching your transistor on, but if you utilize them correctly, they can also be responsible that you can select your input impedance. So it's not some large arbitrary number then you can pick your input impedance if you do this correct. Okay. These two capacitors is to block any external DC sources from other systems to influence your amplifier. Later on, they will also be responsible in a different video for your high pass effect into your amplifier, or basically your lower cutoff frequency. And this capacitor here is just to bypass RE1 and or make RE2 visible when we're actually dealing with the AC characteristics, and then RS and R load is either other systems or a resistive load of some sort. Okay, so every system will always have some impedance, and you can model it using this same approach. Right, so some design parameters and specifications. If you are ever asked to design for maximum gain, you're going to use a common emitter with emitter resistor bypassed. And for a specific gain, you will include the second emitter resistor. Right. You will always design for maximum swing, but sometimes this is a specification, and that is just to design IC RC equal to VCE. So that is so that you have maximum swing capability on the output in any case. There's a typical question about this that we will discuss next. Then maximum power transfer, you can have that on the load or on the input of the amplifier. So typically they will go together. And that is just when you select your output impedance to be equal to your load and your input impedance to be equal to your source. So when you have maximum voltage transfer and current transfer, that's why it's called maximum power transfer. Right. So that is one design scenario. The second one would be for maximum voltage transfer. This is to give minimum loading effects of amplifier. Remember, if you pick your output impedance to be 0 and your input impedance to be infinite, that the maximum gain of amplifier and the total gain of amplifier will be equal to one another. So this is a way to design towards that goal, and that is just to pick your output impedance to be much smaller than your load and your input impedance to be much greater than your source. Typically 10 times greater or 10 times smaller will do. Okay, we're not going to do example on this, but I have it included in one of the designs for today. And that is when you need to design for a specific loaded gain, and you will encounter this a lot, that you have R load prime. So typically some load is given and some total load is given. So that's just R load in parallel with RC in a design. And that will give you will not be working with AV0 from the beginning, you will be working with AV, the loaded gain. Okay. So yeah, just a note, if input impedance is not specified, you can just go with a rule of thumb, and it will typically generate a large enough input impedance in any case. Now, the year-old question that I've been answering a lot in my life is when to use VCC over 2, VCC over 3, and then there is the odd case. If you have a configuration where you only have 2 components on the output, dividing VCC between these two is kind of the obvious choice. Right. Then the one where most people make the mistake is with a dual rail like this. Now you can draw a line right there. This emitter resistor and the negative rail is responsible for your bias. The amplifier part is up here with VCC. So this configuration will also be VCC over 2. Right. Then the last one is when you have the emitter resistor included and only one rail. And with that, it is best to divide the voltage into 3. So that is the VCC over 3 case. Right? But obviously, RCIC and VCE should always be equal to one another. Always try to have this. That means that our emitter voltage can be different. Okay, so it's this case right here. That is when people want larger gains with increased collector resistor or a larger possible output swing. The problem with this is you have decreased bias stabilization because you decrease the voltage here. So that stability goes away. Okay, but this is done in many occasions. So one of our problems, we will actually implement it with a different VE, so you just can see how the design differs. And in that case, your VCE is still equal to your ICRC, but the only thing that you need to do is you need to subtract the emitter voltage from VCC before dividing it by 2. And you also use this technique when you use one emitter resistor to take over the role of bias stabilization and gain stabilization. Just requires a bit more equations to do that, or that you're going to solve simultaneously. So those are the basic scenarios that you get, and I don't ever want to see again in my life people using VCC over 3 for a configuration like this, or using VCC over 2 for a configuration like this, or VCC over 3 when we have a dual rail. Okay, never in my life do I want to see that again. Right, so the common emitter summary that we have is input impedance is base resistance parallel to transistor input impedance, and the gain is GMRC in the end. Typically with the designs we neglect R out of a transistor, so our assumption is that the early voltage is infinite. You can work with this included. It will just appear in your output impedance in general, and later with the simulations you will see that the gain is a little bit off, but not by much, and that is because we decided to neglect the effect of R out of our transistor. Okay, then the equations or typical equations for the common emitter with the emitter resistor included is we have this large input impedance equation right here. Our output impedance stays the same, and our gain is just stabilized and or reduced with 1 plus GMREE. Okay, and a BB and RE like this is just to say that if we have parallel combinations or serial combinations here, parallel combinations or just one resistor, that RBB takes the place of that impedance. Right. Loading effects, always remember that the total gain is these voltage divisions of a maximum gain. Matched input impedance, half AV matched output impedance, same half AV0 and the input like that. And if both are matched, we have our total gain is a quarter of the maximum gain. And this will help a lot when designing for matched impedances. And this equation is nice to remember when designing for maximum voltage transfer, and you have opportunity to select your input and output impedances. It will assist greatly with the design. So our first example, and there is various biasing structures out there. You just need to select the proper one to work with when you're designing from scratch. So one appropriate to the system that you're working in. But there is a whole video on biasing structures. So I just selected these arbitrarily towards the specification goal that we have, and that will become a little bit more apparent in the design, and some of the design is to show you some flaws. This first problem, we're going to use a VCC of 15 volts, a load of 10 kilo ohms. We're using a 2N quad 2 transistor, so beta of 200. And we have three specifications. This one is going to be with all our problems, is to select E12 resistor values. This one we need to design for maximum transfer to the load. So we have some specifics on the output here, and then design for emitter voltage of 3 volts for increased output swing right here. And this specification can come in a lot of forms of giving you a different IC, RC, and VCE value, and then you need to figure out if VE is smaller in general. Okay, so design the resistor values, calculate these small signal parameters afterwards just to verify our design, and let's assume a source resistance of 1 kilo ohm. So what we know off the bat is that our input impedance, so it's a good thing to write down the equations that's relevant to the amplifier. So the small signal equations that's relevant, that's on this side, and then the DC equations, they are on this side. And these will be used as required. Okay, so the input impedance is RB1 parallel to RB2 parallel to R pi. So we can see immediately that our input impedance is very dependent on R pi. So if you ever need to design for a specific input impedance with this kind of amplifier right here, selecting R pi first and then getting a collector current from that is a very large possibility. And then if you selected your collector current first, your VE value might also decrease if you're designing for VCE equal to IC RC. So a different approach is for a specific input impedance here and then designing from back to the front. Okay, so you can approach this from a different end. And that will become apparent with our choice of RS later on. Okay, so basic equations. Then there is emitter voltage given, so we're going to use this equation right here, and VE equals to IE. RE will determine our emitter resistor. So here is the two equations that's going to give us our RC and RE value. And then for our bias resistors, we can use the rule of thumb since there was no specifics given, and that will typically give us a very large value for RB1 and RB2, and our input impedance will be more dependent on R pi. Right, so since our output impedance should be much smaller than our much smaller than our load, we can say that 1 kilo ohm is much smaller than 10 kilo ohms, right? And Z out is our ZC, so we can choose our RC value to be 1 kilo ohm. So this gives us our choice of collector resistor. Right, then our emitter voltage was specified as 3 volts. And we can plug it into this equation and find our Q point as 6 milliamperes. 6 volt, 6 milliamperes, giving us a transconductance of 240 milliamperes per volt and an R pi of 800 and 33 ohms. If you selected R pi for input impedance in this case, specifically for this amplifier, from this you will determine your transconductance, will determine your collector current, will determine your RC value, or use your RC value, and then find out what your VE is, and then calculate your VE IERE equation. So you can approach this in that direction for a specific input impedance. Okay, so since it's design, you always need to pick a point and work from there on. If a specified input impedance for this particular amplifier was given, I would have started with R pi and worked backwards. Okay, towards something that satisfies this specification right here. Okay, in the end, you can't teach somebody to design. Design comes with experience. But knowing your small signal stuff and knowing your DC bias stuff, it will become easier to design. Okay, in general, when selecting resistors like the emitter resistor, I will not recalculate something like the VE voltage. I will just continue working with the voltages that I selected. I am just showing that for a more accurate result in the end, you can recalculate some of your values after you have chosen a component. So the emitter resistor should be 500 ohms. Selecting 560 ohms E12 will yield a bit of a different voltage on our input, our VB value. So without this recalculation, this value would have been 3.7 volts. But the E12s that you select would have been exactly the same would you have continued with 3.7 volts right here. So in the end, it doesn't matter so much to work with 100% accurate values for these voltages. You know that your emitter resistor bias stabilizes your bias, and it will be in the range that you selected. So in practice, you would typically design this, plug in the resistors, and do the simulation, and then knowing what each component's function is, you can tweak your amplifier afterwards. But knowing beforehand what the function of each component is will also help you to make the correct choice. Should this be 470 ohms or should it be 560 ohms? So choosing this resistor less will decrease the current. Choosing it upwards will choosing it less will increase the current, and choosing it this way will decrease. Anyways, knowing that this one is responsible for the bias will help you with your choices. Okay, applying the rule of thumb, so taking the collector current, dividing it by 10 gives us 600 microamperes. So in the branch, here we decide that there is 600 microamperes that needs to flow, and the current here is so small that we do not care about it and ignore it entirely, because the purpose of these resistors is to give a specific voltage and have enough current to actually supply the transistor, but we can neglect the amount of current that flows into the transistor. So that is what the rule of thumb is based on. As long as this 10 is much smaller than our beta value, the rule of thumb will work. Okay, so 10, as I said in a different video, is just a comfortable value that most people go and work with. You can even go with 50 here and it will still work for this amplifier. Going with 50 will increase these resistors a bit more. And as I said, they are responsible for this voltage division and a little bit of current to be delivered into the base of a transistor. So these resistors become larger, our input impedance will move closer towards the value of R pi here, because it will be the smallest value in our design, so in our input impedance. Okay, so solving these two equations simultaneously, we get 6.8 kilo ohms and 18 kilo ohms as our E12s. Okay, determining our maximum gain is just GMRC, so 240 volts per volt. That's 47.6 decibels. I'm going to calculate the dBs every time because that's easier in the simulation to show us our amplifier, how accurate it is. So 240 volts per volt. Then you can calculate R load prime, and for AV just substitute R load prime here in the position of RC, and that will be your loaded gain. And 240 is very close to this 218 right here. Okay, and we did design for maximum voltage transfer to the load of our amplifier. So these are supposed to be close to one another. Okay, so whenever you get the R load prime, that is where you apply it. You just add it into this AV equation right here. And note that using R load prime is using this is the same as having this equation added to your gain. It yields exactly the same result. Okay, calculating our input impedance, since we need it for the total gain, we get 713 ohms. So increasing the ratios of our base resistors, this will increase just by a bit, but again, specific input impedance for this kind of amplifier, R pi is your best starting point for your design. Total gain, including the effects of RS, will drop our gain to 90.74 volts per volts. And note that our output is inverted. Okay, because I work with absolute values here. Just make the calculation of our decibels much easier. But you can see that this small impedance here with a large load on the input side, or a large RS, is not a good thing. Okay, but that is our amplifier designed. So we have a very large gain. It does cater for maximum voltage transfer, but the input is a bit bad, for a lack of a better word. So let's jump into the simulation and check our results. We always check our results in simulations, so let's do that. Alright, I've set up my simulation. Note for the capacitors that I just used very large capacitor values. The design of these will be at a later stage. And here is our final design results. So let's start by checking the DC characteristics first. .8 milliamperes, that is close to the 6 that we designed for. And we just subtract the node at the bottom here, that is close to the 6 volts that we designed for. Okay, so that is our two DC design points reached, and here I inserted the maximum allowable VS value that I calculated off screen. You can do that with the help of video 6, I think. And we see that we have a fairly large output swing from just this 24 millivolts input, and this 24 is when we are still operating in the linear range. Okay, let's check our gains if we reached our other design specs. Okay, this is our loaded gain or our total gain, so that should be our GV. That gives 38.1 decibels, so that is a tiny bit less than we designed for, but it's close enough. That is due to component selection and unaccounted parameters. If we reduce this to 1 ohm, we will get our loaded gain 46.8, so we calculated 45.1, so the difference for the first one and this one is kind of the same, so 45.13 decibels, and then our maximum gain is 47.6 and this is 45.9, so the difference between these two is not that great, which means that we actually did design correctly for output voltage transfer to be at a maximum like that. So that is a simulation, and we do get all our parameters like we designed for them. So let's go over to the next example. For our next example, I picked a dual rail application here, and it is a split emitter. Always remember that this can also be a series combination, it doesn't have to be parallel. Then there's some different implications of how you run the equations, but that was discussed in analysis and in biasing structures. So the examples are purely to demonstrate how we would approach certain problems. And for this one, we have a source resistor of 4.7 kilo ohms and a load resistor of 10 kilo ohms. VCC absolute VEE is 10 volts, beta of 200, and we must design for a specific input impedance and output impedance, so maximum power transfer in and out of an amplifier, and a specific gain of 20 volts per volts. So from this would be the best approach for a amplifier design. So let's jump into the solution of this problem. So first off, again, writing down all the equations. Increased input impedance and our gain with a parallel combination of the emitter resistors down here is important to remember. There is, however, something extra that we can discuss about using the parallel combination when doing the design. We can eliminate one of these resistors for design purposes. But I'll show you the math. Then VCE is ICRC is VCC over 2. Remember what I said. These two voltages is the swing, and down here is the bias stabilization. So VEE over RE1 would be approximately our IE value. And our RB value can be any value smaller than VBE over IB, or VBE over our Q point multiplied by our beta value. Because this resistor here is only a current path into the amplifier. Okay, this emitter resistor is responsible for our bias. So this is the emitter bias. So this gives us a lot of freedom when designing for a specific input impedance if we can select our RB very freely. Okay, so maximum power transfer means that our input impedance and our source and our output impedance and our load should be equal to one another. Output impedance then relates directly to our collector resistor. So we can go ahead and select that at 10 kilo ohms. We know our VCC value. So half of that's 5 volts. So our IC/RC value is 500 microamperes from that. And we can calculate our pi and GM. Note that our R pi is actually a fairly large value, and this is due to a very smaller collector current. Okay, so whenever you need to increase R pi, you need to decrease IC. But this will also bring along a decrease in transconductance, so that will mean a larger resistor to maintain the gain. Okay, then from our emitter side, since we assume that our collector and our emitter is roughly the same value, we can say that IC Q point is our VEE over our RE1 approximately, and we get 20 kilo ohms, and we select the 18 kilo ohm right here, and that is our bias stabilization done. Next up is to calculate our maximum gain. So our total gain is a quarter of the maximum, since we are dealing with matched input and matched output. So every time that will be a half times AV0 would be your GV. Okay, so we need to design for 80 volts per volts. So if we solve our equation, we have AV0, we have RC, we have GM. RE1 parallel to RE2 is 75 ohms. If we calculate the parallel combination and extract, that should be RE2. Extract RE2, it would be 75.3 ohms, which is fairly close because RE1 is actually very large. And the choice of this component, we can go a bit down because that means that our gain will increase slightly. If we go too large, our gain would decrease a lot. Okay, so it's typically better to choose this one a bit smaller to compensate for losses in your circuit. Okay, and it will usually work out kind of nice if you choose this one downwards. But the approximation that I made here can also be used in some of our other steps. Whenever RE1 is much greater than RE2, you can just eliminate it from this equation and the input impedance, because the value that you get is close enough, and you're in any case going to choose a different value that differs quite a lot from this one. Right. Next, we get to the input impedance. And first thing we can do is we can calculate our maximum RB value, and that's 280 kilo ohms. So anything less than this would work out fine. Then our input impedance, we can apply this approximation of a previous step and eliminate our RE1 value. And if we design for specific input impedances, it's best to work out that part of the equation first, and we see that this is 23.6 kilo ohms. Now, Zin is approximately equal to our RB value if RB is much smaller than this monstrosity right here. But we need to design for 4.7 kilo ohms, and this value is not much greater than 4.7 kilo ohms. This is about 4 times, and I would like to see at least a 10 times difference before we can call it much greater. So if this was 47 kilo ohms, I would be happy using this approximation right here. So in this problem, we can't do this. We need to work with the whole equation as is. So 4.7k is equal to this monstrosity, and we already calculated this as 23.6 kilo ohms. And RB calculates at 5.86 kilo ohms, which is much less than 280 Ks. Select the value 5.6 kilo ohms. And if we recalculate our Zin, this is 4.53 kilo ohms, which is fairly close to the 4.7 that we are designing for. And that is all our components calculated. Now on to the admin side. If we calculate our maximum gain, so GMRC, so the top part of this equation is the maximum gain without the feedback, is 200 volts per volts. Okay, so 200 is much greater than 80, so we can apply this equation. It would be better to do this test earlier on in your problems, but it would have become apparent when you were trying to solve this equation right here. Okay, so calculating the maximum gain using RE2 gets us 84.75 volts per volts. AV0, 80 volts per volts. Great. Adding the loading factor on the output, 42.9, matched output impedance, so that should be half. And you'll note that there is a 6 decibel drop every time, roughly 6 decibel drop from stage to stage, because 20 log of 0.5 is minus 6 dBs. Okay, so every time you just subtract 6 decibels from this. But yeah, adding the loading effect, 42.9 volts per volts, adding the input loading effect, 21.05 volts per volts. And you'll note if we chose this upwards, these gains would have all been much more, or much less rather, than our design specifications. Okay, so we did reach our design spec. Let's jump into the simulation and check if all of these work out in a simulator. Right, my simulation is set up. Let's run this. Let's delete this little pathway here first. Now we can see the DC. So we had to design for roughly 500 microamperes, sorry. And this is fairly close to that, 520. And our VCE value was at 5 volts. So if I just subtract this node here at the bottom, that is very close to the 5 volts that we designed for. Okay, let's check the AC. So here is our output. No distortions. Again, using the maximum allowable input. You can calculate from a different video. Our input going in here is 10 millivolts, and here is about 50. So the drop going in is actually kind of large. Okay, but we have increased input range due to the emitter resistor right there. Okay, now on to the AC to check if our gains worked out correctly. This is the total gain that we are viewing, and it works out here in the center at 26.5 decibels, and that is almost spot on from our design. Okay, if we make this load on the input go away, 32.4, it's pretty close to 32.6, and maximum gain 38.3, 38.5. So I would say this design actually works out quite well. Let's go on to a next example. Right, our last and final example here asks us to design for maximum voltage transfer into and out of amplifier with a specific gain. So it's very similar to the first problem and the second problem, and this time the assumption that we wanted to make in the previous one with the base resistors will actually work out. I'm talking about this part right here. Oh, just as a comment before we continue, if we would have worked out this equation using only RC over RE2 right here, the gain would have worked out on 147 volts per volts, which is not even close to the 80 that we were designing for. So that's why we don't use that other equation that I mentioned earlier. If you don't know what I'm talking about, it's good that you already forgot it. Anyways, moving on with this example. Maximum voltage transfer, specific voltage. Okay. So again, equations, we just use a voltage divider bias here, but further, most of these are the same than the previous problem. It's just the extra base resistor. And note that we are not using rule of thumb again, because a specific input impedance is implied with this maximum voltage transfer right here. Okay, so don't always just go with the rule of thumb. There is exceptions to the rule. Okay, input and output impedance. So Zin must be greater than Rs. So 150 ohms, 1.5 kilo ohms is larger. Can typically go with anything larger than that. 10 times would do, 20 times would do, as long as the specification is reachable. So the bare minimum that we can go with is 1.5 kilo ohms. I would typically select that a bit more in a practical example, but let's go with the 10 times so that you can see the effect that it's going to have. Okay, output impedance smaller than the load, 33 kilo ohms. I would go with 3.3 kilo ohms then for our output impedance, and that will also be the selection of our collector resistor. Okay, nothing was mentioned about VE or increased output swing or whatever, so the three voltages here we can choose the same. So we have VCC over 3 on 18 volts, that is 6 volts. And note that due to this, our collector resistor and our emitter resistor will be the same value. Okay, from that we can calculate our collector current as 1.82 milliamperes and get our small signal parameters. Note we have a larger current again, so our R pi decreased and our transconductance increased. Okay, since we want to work with minimal loading, to find our AV0 value from a GV, we can use this equation right here. We know the approximate values for the Z in that we want, we know the Z out that we want, the source and the load is available, and we were specified for a specific GV. So this is 1.5 Ks and that is 3.3 Ks. So we can calculate our AV0 to be 36.3 volts per volt. And note that this is very close to the 30 volts per volt that we are designing for. Only 6.3 volts per volt difference. Right. So since that is the AV0 we're designing with or for, we can calculate our small emitter resistance, and this is 77.2 ohms, 79.5, and you will see that this approximation would have been true again, and we choose it downwards at 68. Going to 82 wouldn't be much of a difference. We can test that in the simulation a bit later on. If that has a huge influence, might actually help out this design to go to 82 in terms of input impedance. So yeah, but let's go with 68 to begin with. Now we have voltage division on the input, and note that I don't calculate a new VE value like we did in example 1. In the end, it doesn't really matter as much since we select E12 values and everything changes in any case. So this will give us our first equation for RB1 and RB2. The second equation for RB1 and RB2 will be coming from our input impedance. So let's see what this back half is equal to, and that's 16.42 kilo ohms. And we want our input impedance to be 1.5 kilo ohms. There is a factor of 10 difference between the two, so I am going to use this approximation of Zin being approximately equal to the parallel combination. So in this case, we can use this. It just removes a lot of the maths for us. And always remember that we can rewrite the parallel combination to be RB1 RB2 over RB1 plus RB2, which will make it easy for us to use these two equations together. If we multiply this top equation with the inverse, the RB2s will cancel, the plus RB1 plus RB2 will cancel. We will be dividing with 1.5k here, and this will result in our RB1 value. Okay, so 4.03 kilo ohms, 3.9k is the closest. RB2, 2.43 kilo ohms, 2.2 kilo ohms is better than choosing 2.7 in this case. If you choose this too high, the current flowing will be a bit too high. I think, yeah, I was playing with these two values, so here I have a different RB value in. So yeah, calculating all our parameters in the end. The maximum gain available without feedback 240.24, which is larger than what we want. Recalculating the maximum gain gets us to 40.37, so that's a tad larger than what we designed for. Adding loading effects 36.7. Our input impedance, if we calculate it using this equation right here, is 1.3k. It's close to 1.5. So that is our new input impedance, and that brings our loaded gain or our total gain to 33 volts per volts. So let's jump over to the simulator and check our results. Right, so here is our simulation. Let's first do DC. Let's run it. That the collector current is 1.75 milliamperes. On this side, closer to 1.8. And if we make this 2.7 Ks, it will go closer to 2 milliamperes. Okay, so that is why I went with a 2.2K in the first place. So that is for our Q point, or our collector current. And 6.4 volts for our VCE value. So fairly close to what we designed for. Let's look at this with the actual signal. So 60 millivolts, 66 millivolts input. So this is again calculated maximum. So only a very small signal entering our BJT in any case, but that is our gain, and this is before we have any distortions. Okay, so let's go over to the AC and see if we meet our design specs for maximum voltage transfer. Right, so our loaded is 30.35 decibels, simulation 30.24. Let's check what would happen if we change this into 82 ohm resistor. That yields 28.9 decibels, which is roughly, well, roughly 28 volts per volts. Yeah, 28 volts per volts and 28 decibels is actually one of those values that is on top of one another. So yeah, so that will decrease our gain too much if we select this 82. So let's go with the 68. Okay. Let's check loading effects. Input loading removed. 31.3 we have 31.2 roughly. It's close enough. And removing the output load, 32.1 dBs. So we actually reach our specifications quite well. And you'll note that we designed for a specific AV0, and when applying our loads, the gain is actually very close to the original gain that we calculated and or designed for, because we are focusing on maximum voltage transfer. Okay, so any load higher or any source smaller, we will be more in this range of minus 40.37 volts per volts. Oh, and as a side note, I forgot. Taking this collector resistor and dividing it by this emitter resistor will yield 48 volts per volts. Remember that equation that I said we shouldn't use? 48 is much closer to the AV0 right here, but it is not close enough. Okay, there is still 8 volts per volts missing or not accounted for, but it yields a better approximation of what your gain would be. But in this case, RE and our transconductance makes our how can I put this? Makes our GMRE greater than 1, but not much greater than 1. Okay, so this amplifier, due to the fact that our REGM is actually a great value, will be more temperature stable than our previous problem. Okay, and that's it for designing. So as long as you know your equations, AC and DC, and understand what the specification is, what's being given to you, designing shouldn't be difficult. Okay, but then again, designing comes with practice, and then you need to practice a lot. So the DC analysis and the AC analysis part should be part of your foundation. It should be in the back of your head always, knowing which components would affect what parameter. Okay, you shouldn't wonder about the analysis anymore. If you're very good with analysis, you would be very good with the design. But if those two fundamentals of analysis, AC and DC, are lacking, designing would be very difficult. Again, I can only show you how to manipulate some of the parameters. There is a formula behind this, but the intuition of when to use what and when to adjust which value comes with practice. Okay, and that's it for common emitter design. Thank you for watching, and I hope this was very, very helpful. See you guys in the next video.